Welcome. This is Mark Anderson from Staties. I'll be talking to you today about achieving utmost reliability via DOE. I welcome everybody attending. It's a bit of a smaller group than usual on the live side of things. However, this is also recorded and then we'll post it on the YouTube. So welcome all of those that come on later and view this via YouTube. So I'll go ahead and toggle over to my PowerPoint presentation and begin the show. Okay, so this is a little bit off the beaten path of what we normally talk about. My background is chemical engineering. I'm a professional engineer in the state of Minnesota. And I also did a lot of work in plant process improvement and became a certified quality engineer. And certainly reliability fits in very strongly with certified quality engineer. But as a chemical engineer, of course, we're working on reliability to try to get our processes lined out. But oftentimes, reliability, you're thinking more of some hard good, like this chain and trying to keep the links from breaking, electronic equipment, mechanical equipment, and things like that. It is a very strong area for the application of design of experiments. And so what we've done is we've achieved a little bit of a focus on reliability through our new Statis 360 software and a Python application that you can interface and use things like Weibull distribution and that sort of thing. So I wanted to make you aware of what we have and also taking a broader view of reliability, not just for hard goods, but also stuff like chemicals, paints, cosmetics, the type of things us chemical engineers would work on. So again, welcome. I've got the attendees on mute. If you would please write down your questions as you go and then email them directly to me afterwards. That would be best. That way I don't have to break up my presentation to take on questions during the talk itself. And of course, that gives me a little more time to think about your question and give a good answer. This presentation is posted in the format of the slides themselves, but also you would get a link to a YouTube presentation to follow up if you would like, or pass that along to other people that you think might be interested in listening to my presentation. So talking points for this presentation would be to provide a briefing on design of experiments, which of course we abbreviate DOE, for rapid and effective screening, looking for the vital few main effects that affect the reliability, characterization of the two-factor interactions in particular, which could be very important and could cause reduction in reliability or improvement, and then optimization of the factors affecting reliability in particular. And then I'll demonstrate how two-level factorials, split plots that handle hard-to-change factors, and responsiveness methods, or RSM, enable reliability engineers or other engineers like myself to achieve high-level robust performance, which we all want to accomplish. So really anyone tasked with improving reliability and taking a broader view of what reliability means, which is to be providing a robust performance, will benefit from this presentation that focuses on multi-factor testing as opposed to the one factor at a time. So I'm going to toggle back to my presentation, and I see more and more people have come on here, and so the audience is growing. But again, if you would please press that raise hand on there if you're able to hear me present and you're with me so far, I'd appreciate that. Okay, great. Getting some other ones coming on here, Wayne, Peter, and so forth and so on. And so then there is probably a way. I'm going to see if I can lower hand. Okay. Of course, with software, and I'm sure you're dealing with this from Staties, but all other software is constantly adapting. And about a year ago, they switched the interface on the GoToWebinar, and I'm still trying to get used to it. I have to admit that it's a bit of a challenge for me. It doesn't get any easier as I get more and more quote unquote experience to deal with the changes. And one of the things that we recently did was switch finally to the Windows 11. And I swear that everything is running a lot slower than it did before, but maybe that's just me. So it goes. I won't continue my venting about changes to things in general and so-called improvements. But I can tell you that, of course, and not that I'm biased whatsoever, is that, of course, the Stati software has continually improved, continually added new features, at the same time trying to make it easier to use. And at the moment, we're currently working on version 24, which is in its late beta version, and that should come out soon, and you'll watch for some announcements about that. So here's the agenda. To begin with, we'll talk about the most basic fundamental type of DOE, which is a two-level factorial. And I have a case study, which is classic, and I use it all the time to promote multifactor testing on a bearing life. But it just happens to fit in nicely to the reliability aspect. And then we have a redo on this coming up using this Python app. I won't actually try to demonstrate the Python app because it falls a little bit beyond my comfort level to do a lot of work with Python. But I would suggest that if you have any interest in Python, is contact our stat help team. If you're a user, you're eligible for this. If you're not a user, then you can contact me directly, mark@staties.com. But if you're a user, you can contact stat help at staties.com. And then mention that you need some help on the Python. I'm taking point, and if you mention Python, you can be pretty sure that I'm going to assign it to my colleague Joe, who's our algorithmic programmer, and he's an expert on Python. And then we also have on our team Martin, who's a PhD statistician, and he developed some Python apps as well. So then, as I mentioned, we're going to move on, talk about split plot to handle hard to change factors. We'll talk about response surface methods for process optimization, product improvement, product optimization, and I have a case study there that's kind of a classic on yarn, increasing the cycles to failure. And then we'll conclude, and then I have an encore, which, if time allows, I'll present, but at least I'll show you where it is. It's a software tutorial on battery life. All right, so this is kind of my standard pitch about this bearing. And the bearing that's shown here was the final bearing that has this plastic raceway. And so it was quite an improvement by a company called SKF based in Sweden. And they had a fellow named Christer Hellstrand who took training from George Box in Madison, Wisconsin. I also took this training in the mid 1990s. It was quite good. And happy to say I spent a week with George Box providing training along with some of his colleagues. And that was awesome. So when Christer came to Wisconsin, he realized that the Swedish engineers, when they tried their one factor at a time approach, were bound to fail unless they got really lucky by simply just looking at one factor, which was called oscillation, that they thought would be most important, which would be the radius of the bearings to the cage. So it relates to how tightly those bearings are fit in, and it's called oscillation, and it's called the kiss of the cage. And so they thought for sure if they would increase the level from low to high, that would solve their problem, which was they were trying to get from 17 hours at the baseline, and they were trying to double that life, at the accelerated test conditions. But as you can see from the numbers here, when they increased oscillation from low to high, it did increase the life, but it didn't double the life. And so that was a fail. So they put their heads together and they said, well, our second best idea would be the heat treatment that we put on the bearing, which surprisingly gave somewhat better, but probably just by chance, life, but it also was not doubling. And so that was a fail. And then finally, the last thing was actually the material of the cage, which originally was a metal raceway, and they switched to the plastic. Now, this was not successful in the sense of doubling the life, but the plastic was cheaper, and so there was a win that came out of the one factor at a time approach and was verified in our multi-factor approach. Now, what Christer learned was we could do a design that has two levels of each factor with the three factors and do all 8 possible combinations. And immediately, of course, you can see here in the upper right, they realized that there was a two-factor interaction between A and B. And this created a breakthrough improvement. Now, there's a funny thing that happens, which I can show you in the case study when I bring it on the computer, is it looks like at these conditions at the upper right corner that going to the plastic actually increases the life, but it turns out because the variability increases as the level goes up, that that's not necessarily significant. So let's take a look at this. I got the reference on the bottom here. So I'm going to toggle over to States 360. Now, States 360 is something you are going to want to use for reliability because it does incorporate this Python script editor, and you have access to the world of Python, including an application that Joe wrote to do Weibull distribution and Weibull regression. Normally, I would tell my clients working in R&D that they might get by with Design Expert, which is encompassed by States 360, and they may not need to have this Python script editor, but here for the reliability, this is going to be important. And so let's take a look at the bearing case. I'm going to open that up. And then I'll rebuild this in just a minute, but I want to first do a little ping back to my list here, and I am going to ask again if you would put the hand up if you can see the screen on States 360. All right, a number of people have put their hand up, so far so good, and bear with me. I'll be asking you that, every few minutes or so, just to make sure we don't get cut off at some point. It's very aggravating. I learned early on when we pivoted over to Zoom and started doing GoToWebinars more frequently. And I was doing, actually, I think it might have been a Teams call back in 2020 when all this really, hit the fan, so to speak, with the pandemic. And I realized I'd been talking for about 10 minutes and the whole time the internet had been down. So that's the reason I'm a little bit, let's say, obsessive compulsive about asking for you just to raise your hands up like that. Now, the design that we have here is the most fundamental design, a two-level factorial. And I can recycle this, reuse it, rebuild it, and show you that this is in our classical design builder with the white diagonal being the full factorial designs. 3 factors would be kind of a minimal design with 8 runs, 4 at the low and 4 at the high for each of the factors. I would try to get to at least 3-factor design. You can do 2 factors, but if you do that, I would replicate it to do a total of 8 runs, and then you might as well throw a 3rd factor in. Now, this design does not have center points in it. Normally, if we're working with numeric factors, which might have been the heat treatment, we're not told because of confidentiality exactly what that was, that we would want to do a middle heat treatment, not just a low and the high. Obviously, a categoric factor like metal versus plastic, there's no middle of that. And so, this design was what they ran and it worked. So, hooray, let's not criticize it. So here we see that we've entered in the names. We've entered these factors all as categoric because we just are told that there's a standard versus a modified oscillation. Normally, I would put a numeric value in that. The same for the heat, as I mentioned. And then the cage is truly a categoric factor, either metal or elastomer or plastic. And then we have the life in hours. And normally, before we do an experiment, I would look at what are you trying to accomplish here? Well, they're currently starting at 17 hours. They would like to double that at a minimum. So I would put 17 hours in here for the difference to detect. We don't want to miss that. And then I would ask, what's your normal variation on life at accelerated testing? And I'm just going to throw a number in here. Let's say 5. If you do this over and over again. And so what we're interested to see with only 8 runs is it likely we would detect that difference of 17. And if I've got these numbers in here correctly, then it's providing some assurance and confidence that even with only 8 runs, if there's a big effect there, from changing these factors in a fairly radical way, we should detect it. So now we build up the design in random order, and I'm just going to simply reopen that file. And so now we'll be able to see the results. And then I'm going to do Control Mouse Wheel to make this bigger, which is a nice feature in the program, so that we can see this a little bit better. And then what I would do as soon as I get the data is look it over. And what I like to do is just sort the data and try to get an idea if in here there is that increase of 17 hours, which there is. And is the range much more than what we would expect by chance? Yes. So therefore, we could basically just pick the winner and say it does look like if we modify the oscillation, we go to the high heat treatment, and then maybe it doesn't really matter whether we use metal or elastomer, the plastic. However, being that the elastomer is cheaper, I would pick that. And it looks like we're going to get a pretty good outcome. And then, because a graph is always much more informative, I like to say, although this isn't true, that Confucius said, one graph is worth 1,000 numbers. I don't know if that's a real saying, but I feel like a graph is very powerful. And so here we can see, because these are treated categorically, we just see an X in here and we don't get the normal color coding that shows the amount of correlation. But you can see from the graph that going to the modified oscillation seems to create a big increase, as does the heat. And then the cage, maybe is not having much of an impact. But these are only main effects. We're not really able to see the two-factor interaction. So we need to go to our analysis node and bring up this half normal plot. And you can see it's been pre-selected and saved. But if we were going to start over again, I would definitely focus on these ones off to the right, keeping our eyes on the prize on an absolute scale. And we could pick these one at a time, but with these orthogonal designs, they're not going to shift around. We can independently estimate each of the effects. So I normally just drag over and lasso the puppies over here to the right. And then immediately we see on the Pareto chart that these are at least above the t-value limit, uncorrected for pairwise testing at p of less than 0.05. Now they're not going above this Bonferroni limit, which is a more rigorous level, but normally I would pick effects that do go above the black line and not pick the effects that are below the black line, but rather put those into the error pool. Now what happens with this is because the life was increased by such a great amount, it turns out that there's some issues with the fitting that pop up. To start with, it looks very good for p-values, and the adjusted and predicted R squared and adequate precision are all very good. But when we go to the diagnostics, then we see some things on the normal plot of residuals certainly would not pass what we call the fat pencil test. It's not in a straight line. We see on residual versus run the potential of two outliers, which I highlighted, and they're actually the two biggest life results, which is alarming. But then what really tells the story is if we go to the Box-Cox plot, we see that it's recommending a transformation via the log, where this green line is at the 0 point, which is a power law, and it's a placeholder for the natural log. And as you see, George Box developed this along with Cox. We try different transformations: inverse, cubed, inverse, squared. Inverse on the other side, cubed, squared. The current transform is no transform, which is everything to the power of 1. But in this red zone, we're going to do better to reduce the residuals. And so what I did was I used this plus key, which creates a new node, just to show you how that would work. And I'll delete this one. And so I created a second analysis to model in the log scale. And I renamed this so we can identify it. And interestingly enough, this is a classic case of where a transformation helps us. We see the same three effects off to the right, but now they're much more significant, as you can see already on the Pareto chart. And then we also see that the p-values are better, adjusted predicted r-squared adequate precision are better. We're now in the zone, and therefore we get a nice residual plot on the normal paper that falls on a straight line, via the fat pencil test. And the two apparent outliers now are well explained. And so this is kind of a cool example of how multi-factor testing, two-level factorial DOE, was applied as a reliability tool to accomplish their goal for increasing the life by double. And you can see now that the LSD bar, least significant difference bar, will increase because the variability goes up as the level goes up, hence the use of the log transform. And therefore, we would expect to see a fairly broad range, at this ideal condition up here in the life. And so we can then apply our numeric optimizer, although it's pretty obvious we want to increase the oscillation and the heat. But we can say maximize this, put a stretch target in, and just double check using the software that indeed increasing the oscillation to this modified level, increasing the heat to the high level, will be key. The cage itself doesn't really show a significant outcome. However, we would bias this and say we would really rather have the elastomer or plastic because of it being cheaper. And that gets us to our final solution. So the range of this, if we were to look at our confirmation node, and normally what I suggest is do maybe 6 confirmations, make up bearings with these new conditions. And then you can see that the prediction interval is actually quite wide, because at that high level, the life will vary, quite a bit more. And so that's the reason why we didn't actually see a significant advantage to the plastic / elastomer, but it was cheaper. All right, so I think that about covers our first case. Um, how do you like that? Is that a good story? Yes? Hands up if you think that's a good success story to bring up, Rebecca and others. So I would definitely suggest you take this from what I've presented. And if you're trying to convince people about doing multi-factor testing, this is a really good example to use for anybody, whether they're reliability engineers or R&D scientists or anybody that can take advantage of multi-factor testing. This is kind of my standard pitch that I'm going to make to go from OFAT to the multi-factor. Okay, so moving on then. This is the kind of the happy ending that we show here that, well, although the cage going from the metal to the plastic / elastomer didn't really have a significant advantage, it was well worth it economically to change over. And so this turned out to be a huge success, and it was written up in the year 2000 in a little story called Breaking the Boundaries in Design Engineering. And they reported that this multi-factor DOE led to a 300% increase in SKF bearing service life. Wow. So amazing what you can do if you do a multi-factor approach. Not only is it more effective for detecting interactions, which you can never get from OFAT, it's also much more efficient for looking at many factors all at the same time. So it's a double win. So then when Joe came up with this Python app to do Weibull regression, which is based on this distribution shown here that was developed by this Swedish mathematician, and how you'd pronounce it in Swedish, even though I'm an Anderson, my Swedish has been snuffed out over generations. I'm going to say Waladi Weibull, but I'm sure it's more of a V sound, was the one who developed this and presented it to these mechanical engineers. Again, this gets a little out of my area being a chemical engineer, but it's frequently used by reliability engineers to assess time to failure for systems and parts. So Joe developed this Python add-in that works with our SATIS 360, and then reanalyzed the bearing, which of course was made also by Swedes, via Weibull modeling. So what I'm going to say is that rather than make a daring attempt to actually demonstrate this if you are interested, is to contact stathelp@staties.com, and then I'll have Joe follow up with you. But as we mentioned, we have this Python icon, and then we have under the help system, once you get into this Python tutorial, and this is the way I would start before you go back to Joe, is see if you can get your Python environment set up. And then once that's set up, you connect it to Staties, and then you can execute the script, and go on from there. Okay, so this lays out the whole process that you can go through to get connected up to the Python. All right, but I'll just show you what happens when we redo this case study using Weibull regression. And it turns out that we get the same model, which is A, B, and the interaction of A, B. But now, of course, we're not doing a transformation. We're using a special regression tool instead. And then the equation is down here. Now, what I was interested in doing is seeing bottom line, do we get the same interaction using the Weibull regression? And we do, but the only difference is that we don't have these LSD bars in here. So from my perspective, this is a case where probably we could just do the normal ordinary least square regression with the transformation applied, of course, is the key. However, it may be well worth looking at this both ways, especially if you have censored data, because in a case like this, you might create bearings that last for so long, like years, you're just going to have to cut off the test even though you haven't completed the final result. So this, I think, is going to be a good tool if you're working on reliability studies like this bearing case and other types of things. For example, I've recently been involved helping a company that does flame retardants defend a European patent, and they came up with a combination of 3 ingredients that makes the burn test last so long that they just can't even keep going with the burn test. It just never burns. And so they had to cut it off at a certain point in time. And that's an example of censored data. Okay, so now we're going to move on to split plot as another type of tool that reliability engineers might make use of. And if you're not familiar with this split plot, it's very handy for hard to change factors. And one real common one is oven temperature. Let's say you're going to powder coat a part, and then you're going to put it in an oven and bake it, right, to get it to set up on your part. And that was actually something I was experienced with at one point in time. I was involved with a medical device company. We had stamped out metal tanks that held a molten paraffin in this bath that we created. And we did the powder coating, and then we had to put it into a chamber, heat it up, and then it was set, and then we could, assemble the part. So split plots, again, if you're not familiar with this, first of all, the term relates to the development in the fields of agriculture. And it was actually agronomists that came up with this. And of course, one of the more famous agronomists that is instrumental for stats and DOE was Ronald Fisher. And so he was instrumental in developing DOE as a whole, but they developed a tool that became very important for dealing with hard to change factors. Excuse me for a second here, a little glass of water. And in this particular scenario, they had application of a herbicide, and they had a large area of land called a whole plot. Within that, they created these subplots, and they had various crops that they applied in a random order: corn, potato, and squash. This one on this whole plot is randomized a little bit different: corn, squash, potato. And then we see potato, corn, and squash on this one. Now imagine an airplane. My drawing abilities are very poor. Um, but this airplane is coming down, and on the airplane is a tank, and it's got various herbicides associated that we can spray. And so the first time the pilot comes over at random, chooses herbicide B. Because of the way it's sprayed, you've got to spray it over the whole plot and encompass all three subplots. And then there's a buffer in between where the plane comes around, switches the tank. The second pass is herbicide A, and then it comes back around. A third pass is herbicide C. So we've actually restricted the randomization of this factor of herbicide into the whole plot. So it's a way of grouping that does create some repercussions in terms of the powers that you have to detect effects, but as a convenience, it's about the only way to go. And what George Box would say is that randomize what you can. If you have hard to change factors, work with a split plot. And then if you can't randomize or do a split plot, just do the experiment anyways, but still do a multi-factor approach. Box felt like in the end, it's still better to do a multi-factor even if it's completely grouped together in a way that it has no randomization. So I like the way that George Box thought from a practical perspective. So what we have to be careful about here is that although it would always be convenient to group certain factors, always there's some that are harder to change. Don't do it unless it's almost impossible to randomize. Things like oven temperature, because you're going to pay a price by losing power to detect the main effects of these hard to change factors. And the interactions within the hard to change, if you have more than one hard to change, also will lose power. But the good news is that though the main effects that the main effects of easy to change factors actually become easier to detect. In other words, you actually gain power on the easy to change factors because they're protected from the influence of the hard to change. Likewise, the combinations of easy to change will also be higher power. And surprisingly, and there's some math behind this, the interactions of hard to change and easy to change also gain in power. Thus, I feel as a chemical engineer and for reliability engineers also, that these split plots will provide a very sensible alternative to a completely randomized design or CRD. So don't be afraid to use a split plot. I would advise that you try to hold off until you feel it's absolutely necessary. So now I'm going to talk about a case study from George Box, and this involves an oven temperature. But before I do, I'm just going to ping back to the group to see if you're with me so far looking at this write up on this George Box study applying a split block. So if you're still there, okay, we're getting the usual nice feedback from various people. So thank you for that. So now let me talk about this case study. So this came about from quality engineering, and there was a period of time where George Box had a column, and I would always read that religiously back when he was really active in the 1990s because he always had really great ideas to discuss. And so let's talk about this particular case study, which led to a highly corrosion resistant coating for steel bars. And it involves some trade-offs because of the fact that they couldn't easily change the temperature in the oven across what they called heats across these three levels. Some compromises had to be made. However, the four different coatings could be put in randomly, so this was easy to change, or what we call ETC factor, easy to change, and this was hard to change, or HTC factor. And so this was giving us a grouping that made it much more practical, this idea of a split plot. And then even easier, he ran the temperature up and then down, which again is not ideal, but I think his idea that if push comes to shove, you have to start giving up on randomization and just look at the actual effect magnitude and worry less about the p-values. So I'm going to take a look at the at this design. And so we'll close out the one that we currently have, and then we'll open up this corrosion. And you can see the grouping here where we have um, these dark lines cutting across represent the break where we switch from one group for the hard to change temperature to another group. And normally this would be randomized, but like I say, George Box realized that his clients would never be able to run a designed experiment if they had to randomize the temperature. So he said, well, look, if you just continue to increase the heat until you get to the top level and then reduce it down for the next three groups. This way we get a replication of the temperature effect, which is necessary to get at least some power on the hard to change factor. And then within each group, you see the coding is randomized. And so it's actually was placed at different locations, I think, on the tray within the oven. So let's see how this analyzes. Now, when I attended the George Box seminar in 1996, it was the first time I saw that you can use two half normal plots. And I love this graphical selection method, and I was very excited to come back to Staddy's and my business partner, Pat Whitcomb, to talk to him about this, and subsequently it got implemented in our software. So that we have the subplot effects shown here. Let's go to the whole plot effects first. And actually, the temperature, because of the replication of the experiment, did pop out somewhat from the pure air, which are shown by these green triangles. And it was somewhat significant. Now, we don't get the Pareto plot because that hasn't been invented for the split plots. Now we go to the subplot next. And here we see that we get the coding, which is going to have more power to it. You can see that it's further off the line because of the way that we've protected the impact of that because of the whole plot has been grouped. We get a real strong indication of B, main effect of the coding, and then the interaction of A and B. And we use a small letter for the hard to change factor and the big letter for the easy to change, just so you can keep track of which is which. And so this is our model. And then using restricted maximum likelihood as a approximation and using the Kenwood-Rogers for the p-values, we can see that the main effect of temperature is not really significant, although it did stand off the line a little bit. But nevertheless, it is significant in context of the coding, and so that preserves the final value of this. Diagnostics didn't show anything unusual. And then here we have this interaction of temperature and the type of coding. And then finally, we can look at this in a 3D surface, and we can see that on these towers here that there's an effect of coding, but it is modified by the temperature. And for C4, we see more of an impact of temperature at the high level to give the corrosion resistance. So maybe that would be our solution, is going with the coding C4 at the high temperature. All right, so that's another example of a response that's reliability. In this case, relating reliability to being corrosion resistant. Certainly, I think that's fair to say that we now have a more reliable process to coat and heat these metal bars so that they will last longer out in the field. And then I think the 3D plot is really informative in this case. So I would say that George Box was a very clever man. How many of you would agree with that and give George Box a thumbs up? Rebecca, Wayne, Peter, others? Okay. Yes, I think there's no doubt about that. Neo, very clever. Thank God for George Box. Thank goodness, I guess might be another way to put it. He really did a great job for the development after his father-in-law, Ronald Fisher, to carry on with response surface methods, which is our next topic, and then do a lot of other things like Box-Cox plot, and just help people like myself look at DOE from a more practical perspective. So now we get into response surface methods. Here we have the famous quote from George Box: "All models are wrong, but some are useful." And the idea of taking an empirical approach to things, is nothing wrong with that, provided, of course, that we apply first principles know-how to begin with to try to understand what's going on, and then start doing empirical studies. And so the idea of response surface methods and the standard design that he developed would be basically a core of two-level design with center points, but adding in these additional points on the outside, which are represented by stars, which are called axial points. And this entire design is what Box invented in 1951, along with a fellow named Wilson. And this is called the central composite design. So this would be something done after you do screening and characterization, and you still have some potential to improve the product or process. Then you're going to want to do this design, which is more complicated with multiple levels of each factor. Now, it turns out that if we have just a couple of factors, for k equals 2 factors, I actually think just doing a 3 to the 2 design, which is a full 3-level design, is not a bad design at all. Because of it being simple, you can explain it to people fairly easily, and you do get enough levels to fit the quadratic polynomial that can fit, rising ridges, simple optimum peaks or minimums, and things like that. So I think that's probably not a bad design. Let's see what we have here on this classic study on factorial experiment on cycles to failure of worsted yarn. Now it says factorial experiment, but if we have 3 levels of each factor, it actually becomes a response surface method. So let's close this out. And then we've got this yarn example. And let's see what it says for the summary. Okay, 3-level factorial design. And this is available in our software under our response surface designs. And you can see we're looking at 3 factors: the length of the yarn, the amplitude of the cycle that was applied to it, the load that was put on to try to break the yarn, and then finally cycles to failure. Now here, if we look at this in descending order, we can see that they were able to get failure on all the yarns. Of course, if this had to be censored or truncated, that would push you back into the question of perhaps using the Weibull regression. But in this case, I think using the ordinary least squares, I always would start by just eyeballing the data on the length, the main effective length, the main effective amplitude. Since these are numeric, we're actually getting a shaded view, with red being a positive correlation. This is a fairly high correlation of 0.623. Blue being a negative correlation, this is a fairly high negative correlation of minus 0.505. And then the load didn't have quite as much of an impact, so that's kind of a pale blue color. And from here, it's just kind of a standard analysis using the polynomial models. This one is already set up in the log scale because of it being such a broad range. And so it turns out to be linear in log. And I think we should be able to see in diagnostics why the log is picked because of the Box-Cox plot. You see it converging very tightly on log. Now, if we were to look at this again without a log, we might see that all models are wrong, but some are useful coming into play here, because now let's say we do this with an as-is analysis. Okay, no transform. Let's see what happens. Aha. So now it says that not only is a linear not going to be good enough, in that we have to add 2-factor interaction terms, but also, furthermore, if we add quadratic terms, we'll significantly improve, possibly even cubic, but that term is aliased. And so it ends up requiring a fairly high order, maybe even quadratic is not enough to get the same fit. Now, what I usually suggest to people is that we can compare the predicted R-squareds between one model versus another as kind of a bottom line, and the adequate precision. So 0.9528 in the log scale and 0.8491. So I would say log is better. But if we look at the actual surface graph, let's say in 3D surface, and let's say we look at the high load level, it's kind of the worst case scenario, and we do the same thing with the same model, but in log scale, and look at that in 3D and move the load up to the upper end. And then look at the two fits as is and in log. And I think it's kind of debatable which model would be better. There's some view here that maybe the as is fitting better at that high cycles to failure, but I think that may be kind of artificial. So either model would work. In the end, I probably would fall down on the side of the log model, which is the first one, and then see what we can do to maximize the cycles to failure with a stretch target at the top. But that's just me, and you could do it your way, and neither one of us would be wrong or right, I would say. Okay, so that's an example of, and I think it does relate to reliability because we're talking about failure of basically a part, which is yarn. And so this demonstrates the application of response surface methods. Okay, so now in conclusion, I hope that this presentation did provide a good briefing. I know a number of the people that are attending, for example, Rebecca as a statistician and others are perfectly familiar with this, but maybe it's something that you could pass along to people within your organization, whether they're quote unquote reliability engineers or not. It might be helpful. And then if any of you are reliability engineers and maybe new to this multi-factor testing approach, this will be helpful. Maybe you guys are coming onto the YouTube later, may not be here live, but I think you'll find this a very useful tool. So I hope you appreciated this briefing and the demonstration that we gave on two-level factorials, split plots for hard to change, and response surface methods, that this will allow reliability engineers to achieve that high-level robust performance. So of course, I've got to ask at this point, do you agree that this was a good briefing for reliability DOE? Okay, thank you. It's the speed that you're putting the thumbs up. I'm appreciating that. And if you've attended my talks before, that I'm not shy about asking for approval. I won't say that I'm averse to getting a nice pat on the back and a plus. At the same time, of course, if there's any suggestions on how I could do better, feel free to send anything to me, mark@staties.com. Just be gentle. But of course, I can always improve, even though I've been working on this for now over 50 years and written these 3 books as a primary author. And I would say the tools that we showed here were primarily would be covered in this first book on DOE Simplified, which covers the factorial design. And then, of course, response surface methods are covered in RSM Simplified. And I didn't really show any designs for mixture, but this is a favorite of mine. And the differences we work with in these ternary diagrams, or sometimes called phase diagrams, are perfect for dealing with optimizing components. And certainly reliability of materials would be something to consider using mixture design for. I think if you were to come back and try to sharpen up your skills, you would do well by this modern DOE for process optimization. We have a class coming up in December, but you can check our website for the current schedule. If you're coming in after the live presentation, check that out and see when we're going to give a presentation. You can also set up a private presentation by contacting our workshops team, and they'll get you set up for a presentation specifically for your group. All right, so then the encore, if time is available, and there's really just a few moments here. Something happened with my slide here. Interesting. Okay, so we end up in the end with this really interesting interaction plot showing how the effect of material on a battery, which can be either material A3, which is this kind of purplish color, material A2, or material A1, will affect the life of the battery in hours, but it depends on the temperature. So if you're down in Phoenix, Arizona, that's one thing. And if you're in Minneapolis, that might be another thing as far as how your battery is going to last. And surprisingly, the batteries seem to last better at lower temperature, or maybe not so surprisingly. So depending on where you're located and what the temperature is that the battery is going to encounter, you see that there's this interaction. Now this study, I can just leave it for you if you have Design Expert or States 360. If you don't, you can download a free trial, and you might want to take a look at this tutorial. It comes from Douglas Montgomery's book, Design and Analysis of Experiments, and it's what we call a multi-level categoric experiment. So in this case, Doug set up this experiment for his client with the three battery types, material types A1, A2, and A3, three temperatures, and they evidently did this in a totally randomized experiment. And then to build up power, they did four batteries at each combination of conditions. All right, and so in the tutorial, you work through the process of how to set this up and where that would be in our software, right? And then there's actually a part two, which is interesting because in the part two of it, it shows how you can take temperature, which was treated categorically to begin with, and using our tool, Design Expert or States 360, you can make it numeric, and then you can apply a polynomial model, which is much more sophisticated to it. And I can show you very quickly, with a few minutes we have left, with the tutorial data on the battery life, how that would be done. And so basically, this factor originally is set up as categorical, which is fine, but it's going to be more sophisticated to make this a continuous numeric. And then when we do the analysis of this, we get into this advanced option to treat the analysis as polynomial model. And now we get this, buildup of fit summary. But what we don't have here is the fact that there is some advantage to putting in a cubic term, and I can trick the program into doing this because I know that temperature is a continuous factor. And so I'm going to put the AB interaction, I'm going to put the squared term for B, and I'm going to force this into a third order polynomial model, AB cubed included, because I can. And it turns out that that AB cubed is significant. All right. And to support that, we do need the B squared to have it in there. If we try to reduce that, I think we would be busted for not having a hierarchical model. And so we could try p-value backward on this, which I like to try at least. And then we can see if the program says it's got to be hierarchical. Yes, it does. And then you can see that even though these are insignificant terms, they come back in again to form a well-formulated polynomial model. And this actually works pretty well. And then we do the diagnostics are fine. And then if I switch the axes so the temperature is at the bottom, then I get this beautiful color banded picture of what happened at the end, and hence this slide here. All right, so that's my encore. It's taken me right up to the end of the time here. And so just give me a final hurrah on your control panel. And then if you would follow up with any emailed questions, and also if you could connect on LinkedIn. Thank you for doing the applause symbol this time around. Again, I appreciate all this positive reinforcement. And now we have this on the YouTube, so you can connect people to that. But please do connect on LinkedIn if you're not already on there. So to conclude again, thanks everybody for attending. It's been a pleasure to talk about reliability and put up these different case studies to show how the multi-factor approach will achieve utmost reliability.